So today I want to talk about finding the dot product, also known as the scalar product. And specifically, I wanted to show you how to calculate the dot product when you're giving the individual vectors A and B in unit vector form. Because we are also taught that finding the dot product of A cross B can be done if we just take the magnitude of each vector, the magnitude of A, times the magnitude of B, times the cosine of the angle between them. So if I have some sort of scenario or some sort of illustration like this, using this way to calculate A dot B is really simple. But when we have our vectors written in unit vector form, and if they're three-dimensional, this is really hard to do. So for instance, if this is my vector A, now remember, 2 represents the x component, 3 represents the y component, and -5 represents the z component. And similarly, I have a vector B that also has 3 components. The question is, how do I calculate that dot product? Because I don't have any idea what the angle is between those 2 vectors. If I think about it, A dot B could be really thought of as taking this entire vector A and then I dot it with the entire vector B, which I could really do by using the distributive rule of taking the 2i dotted with the 6i and 2i dotted with the -j and with the plus k, etc., and do that for all 3 of these terms. Sort of like when I'm multiplying, 325 times 232, I'm doing that distributed thing. Now, when I do that, I'm going to get a lot of different combinations of unit vectors dotted with either themselves or with each other. For instance, if I do this with all 3 terms in the A dotted with all 3 terms in the B, I'm going to get some terms that are unit vectors dotted with themselves. And I'm going to get some terms that are unit vectors dotted with each other. And so simplifying the big old mess that I'd get if I did this dot product the way that I've described can get really much more simplified if I try to figure out what all these terms are. Now, this is where this expression is going to help us out. When we talk about unit vectors, the thing about a unit vector is the magnitude of all unit vectors is 1. So using this format for calculating the dot product would give us 1 times 1, and then it's the cosine of the angle between the 2 unit vectors in this case. Well, in the first line, I'm doing all the unit vectors dotted with themselves. So the angle between I hat and I hat, or j hat and j hat, is just 0. And that is equal, the cosine of 0 is just equal to 1. So all of these unit vectors dotted with themselves gives you 1. However, I get a very different result when I take a mixture of unit vectors, like I dot j, I dot k, etc. Because all unit vectors are mutually perpendicular to each other. So the angle between any 2 of the unit vectors is 90 degrees, and the cosine of 90 degrees is 0. So all those cross terms actually don't give me anything, any contribution to the dot product of A dot B. So simplifying everything, we only get a contribution to A dot B when we have like terms multiplied by each other. So I have AX times BX plus AY times BY plus AZ times BZ. That is really how we would calculate the dot product of these two unit vectors here. So I would have 2 times 6 plus 3 times minus 1 plus minus 5 times 1. So that's gives me 12 minus 3 minus 5. My answer is just 4. And that answer makes perfect sense to me, not that I know whether it was 4 or not, but the fact that it's just a number. One of the reasons that we call the dot product also the scalar product is because of the fact that the answer is a scalar. So I don't care what you call it, but remember that when we do the dot product, our answer is a scalar. Once we've done that, we can actually go back to this expression and we can actually use this to figure out what the angle is between A and B, which I honestly had no way to try to figure out. I could probably work on it for a really long time and maybe figure it out, or I could just do this. Because if we take this expression and we rearrange it, we can solve for the cosine of the angle, that angle being the angle between A and B. Now, keep in mind that the magnitude of both of these vectors can be found through an extension of the Pythagorean theorem. So for instance, A, the magnitude, is the square root of 2 squared plus 3 squared plus minus 5 squared. And we could do the same thing for B. Even though I kind of randomly made up these vectors to do this problem, they both have the magnitude of the square root of 38. Who'd have thunk it? So I put on the top A dot B, which I found was 4. The magnitude of A is the square root of 38. The magnitude of B is the square root of 38. So the cosine of theta is 4 over 38, or we could write it as theta is the angle whose cosine is 4 over 38. And if I do whip out my handy calculator, I find that that angle is 84 degrees. And that's how we can use the dot product.